So, well, first of all, thanks for coming to the meeting. Today I'm going to talk about symmetries in gravitational system. So, well, first of all, I would like to outline say that there are many aspects of gravity, especially in the context of gravity. So today I'm not going to be able to cover all of them. So if you work on something similar and I didn't mention something you work on, I do apologize. So I'm going to just tell you something which I encountered in my research. And yeah, so okay, so let's begin. So well, I'm going to talk about symmetry, but I'm sure that we kind of have like a feeling of what symmetry is, right? So it's like you look at a sphere and you can rotate the sphere and it looks the same. It's like a sphere has some form of symmetry, right? So symmetry is it's basically like a transformation that keep some structure in your system unchanged, right? And it form like a mathematical object, which is called a group, right? And it's also like open like the whole field in mathematics to study this structure, which is called a group. Well, you don't have to have too much about the details. And for us for me in physics, in high energy physics, and this structure that we keep fixed under some type of symmetry is nothing but the physical laws or like your theories, right? Like your Lagrangian, your action, right? And in this case, symmetry is very useful. Let me put it this way. And because it gives you many implications, many consequences. For instance, we have these so-called conservation laws, and this is a very famous theorem by Emmy Noether. Maybe 100 years ago, and I think it's one of the most beautiful theorem in physics. And I think Namba-san already like speak about this maybe a year ago. I don't remember. Right? Yes. Anyway, so well, what the theorem says that if you have a symmetry and your physical law is unchanged under a certain symmetry, then it implies that you're going to have some conserved quantity, some conservations. The famous example is that let's say if your physical system doesn't change under time translation. So let's say, I mean, you're doing physics today, you're doing physics tomorrow, you're doing physics like next year, and you get the same result, you get the same physics. Then it implies that you have the notion of the conserved quantity, which is the energy of the system. And if your physics doesn't change, then under like a spatial translation, you're doing physics here, you're doing physics like in Kyoto, they are the same, then you will have like the conserved momentum. So it's very useful, this Noether theorem. Another usefulness of symmetry is you can use the knowledge of symmetry to classify your physical state. And the famous one along this line is Wigner. This is work in quantum field theory, which kind of classified what are particles according to the symmetry of quantum field theory. And so I would say that, I mean, technically, so quantum particle is nothing but a representation of symmetry group. So it gives you to some extent it gives you like the identity, right? The ID card to particles. So it's like particle can have mass, can have spin, and can have like any quantum number depending on the symmetry group. And another thing is that symmetry kind of constrain the dynamics, the physical process, right? So not all physical process is possible. I mean, some of them is forbidden, some of them are allowed. And what dictates this is the knowledge of symmetry is what people call the selection rules, right? So some physical process allow and also some forbid. And there are a lot of other usefulness of symmetry, right? So well, in short, I mean, what I tell you is just it just classify the state, constrain the dynamics, and also like bookkeeping what is conserved in your system. And today I'm going to talk about symmetry, but in gravitational system. And we know, I mean, the current understanding of gravity is general relativity. So gravity is nothing but the curved space-time. And it obeys the Einstein equation. So in general relativity, you have we can represent gravitational field with this the field which is called the magnetic tensor T mu nu. This field depends on the point on the space-time, and this T mu nu is kind of tell you about the geometry of the space-time. It's also is connected to the gravity. And this T obeys the Einstein equation. And see, and this Einstein equation is kind of invariant or covariant. So the form of Einstein equation doesn't change under certain type of transformation. So let's say if you have you have like a space-time, like a curved space-time here, and then there's a transformation that map a point on space-time to another point, and the Einstein equation is doesn't change the form under this type of transformation, and this thing is mathematically is what people call diffeomorphism. Diffeomorphism, and you know you can.
Thank you.
Oh, okay, sorry, I didn't. So okay, but you can see it now, right? Okay. Well, I mean, you can think of this kind of like diffeomorphism as like a coordinate transformation, right? So it's something like it's like you can pick like different rulers, different clocks, but you can but we describe the same thing. So in some sense, diffeomorphism is something just a redundancy in your description. It's not like a true symmetry. It's not physical in that case. This is what sometimes people call this thing as a gauge. Right, so it's just basically just a redundancy. So it's not a true symmetry. But in some case, this diffeomorphism can turn to be a meaningful notion of symmetry, and that is the case where you have some kind of fixed structure in a space-time. So you put it this way. So if there exists some kind of fixed structure, space-time, then you can have a meaningful notion of symmetry. And now it kind of boils down to what I mean by fixed structure, right? And today I'm going to give you like 3 different layers of this fixed structure. And the first one is well, you just fix space-time itself. So this fixed structure is just the whole space-time is fixed. The whole space-time geometry. And what I mean by that is that if you look at your gravitational field, which is this metric that I told you about, and it doesn't change under the symmetry transformation, and this delta it means like the change of the gravitational field, and this side it's just a vector field. This is like a side, like infinitesimal vector field pointing along the direction of this transformation. So you can think of this vector as a generator of the Symmetry group. And if the space-time is fixed, then it doesn't change. Right? So this is 0. And this is like the basic symmetry you can have in space-time, and this will give you well, for example, in the case of black hole space-time, it will give you the notion of mass and angular momentum of the black hole. And yeah, I would like to put like a year where we first learned about it, but I'm not so sure. I'm sure maybe Christy know about it. But I would say, you know, Einstein put general relativity on 1950, and in 1960 we have the first one solution, is the Schwarzschild solution. So I would put it maybe around 1960, where we maybe begin to think about this type of space-time symmetry. But to be fair, I mean, that tradition already studied this in the context of curve manifold for longer than that. It's the work of Curie. But anyway, in physics, in gravity, it's allowed this here, I would say. So this is like the basic space-time symmetry. Is like the first layer. You fix the whole space-time. Another layer, which is called asymptotic symmetry. Now you allow the space-time geometry to change, but now what you fix is that you fix boundary structure. So because this metric G, this gravitational field has to satisfy the Einstein equation, which is a differential equation, and you have to supply differential equation with boundary condition. And you can have different boundary conditions. For example, you can imagine that your space-time is some kind of like a box. So this is like one solution of the Einstein equation, with negative cosmological constant. But anyway, but this type of space-time can have a boundary, which is the boundary at infinity. I would say it's asymptotic infinity boundary. But then you can kind of do the math so that I can draw it on the backboard. And you can look at this one, and then the whole space-time is empty. But you can also look at another solution of the Einstein equation, which has like the same the same boundary, which is so the space-time look like a box, but in this space-time you can have, let's say, like a vacuum here. And this is also like another solution of the Einstein equation, and these two solutions are connected by this type of symmetry. So this is symmetry connected through. And this symmetry like change what happened inside but fix the boundary itself. And this will give you like a bigger notion of symmetry group, and this is what people call the asymptotic symmetry. And well, the famous example is when people, you may already heard about this in many coffee making talks, but it is a notion of what people call the ADS, anti-resistor space-time, which is like space-time with negative cosmological constant, which is something like a box here. And the asymptotic symmetry of this type of space-time is conformal symmetry. And in some sense, this is like a precursor or a seed for the idea which later known as holography, which is a statement that what happened inside space-time in gravity is kind of can be mapped to the non-gravity theory being at the boundary. But this non-gravity theory has this type of symmetry of asymptotic symmetry of the original space-time, and that's why we later have this ABS symmetry correspondent, which is the duality between gravity in ABS and field theory, which is conformal. Conformal is like a transformation at a certain scale. And this is like a precursor. So this type of asymptotic symmetry is very useful. And the year I would put
Few more.
Sorry.
You have only a few more.
Oh, okay, sorry, I'm going to finish. So I would say 1962, but it's not about ADS, asymptotically fast space-time, but the same picture. And lastly, let me be quick. And this type is what we call the corner symmetry. And this is kind of boiled down to, again, another theorem. Which say that that physical quantity in gravity or in any gauge theory is localized at the corner. And what is the corner? The corner is any four-dimensional true object. So in four-dimensional space-time, corner is two-dimensional. You can think of the corner as a, let's say, as a sphere in four-dimension. For example, like the surface of the black hole, which is a sphere, it can be the corner. And if you look at the symmetry that preserves the corner, so any corner, it doesn't have to be at infinity, it can be at finite distance surface. So you infuse the corner, and if you look at the symmetry, and then you will get what we call the corner symmetry, and let me write for you. This kind of look very well. This one is going to be composed of writing. So S is the corner, so you can think of this as a sphere. So it's your S. And this sphere is two-dimension. If you in four-dimension, then you're going to have two normal direction to the sphere. And it kind of form like the plane at each point on the sphere. So you can have different plane. And the corner symmetry is this one. correspond to the deformation of the sphere, the corner. And this one corresponds to translation. So you can move each point on the sphere along these two directions. So that's why 2 here. And because this translation can depend on the point of the sphere, that's the beginning of the subscript S here. So sometimes people call it super translation. Has nothing to do with supersymmetry. Just we just use the word super for different thing. And lastly, this one is just some kind of linear transformation of this head. And yeah, and this is like the biggest symmetry group that you can have in general relativity. And yeah, infinite dimension, and there are a lot of things that we don't know about this symmetry. For example, how to represent this symmetry in the quantum theory, and that is like a one direction toward like a quantum gravity, I would say, to using this knowledge of symmetry group to construct the Hilbert space for quantum gravity. It's the work in progress, and there are a lot of things that we don't know. So yes, and okay, yeah, I think I will just end with my talk. Thank you very much.
Thank you very much. Question from non-experts.
Yes. Those symmetries are based on fixed structure, you said, and so that is there any examples for non-fixed structure?
Well, if you consider like any general symmetry, but you doesn't fit anything, it's not going to be a symmetry in physics, at least in the sense of energy physics, because it's just some kind of redundancy in the description. It's not a true symmetry. It doesn't change your physical state. Just you keep different coordinates for the same thing. So it's like a redundancy. This is what people call the gauge transformation in physics.
So in such case, it's fixed.
It depends on the theory you have, yes, but it's not the true symmetry. Yes. Like in standard model, you also have this notion of gauge symmetry, but that's more like an internal symmetry of particle physics. Yes. Okay. Yes, yeah, okay.
Yeah.
Okay. So just let me complain for you gravity is space time, so I guess manifold or differential manifold. And
Yes.
for that you are looking for fixed structure.
Yes.
So these are 3 examples.
Yeah.
But are they compatible together, or does it correspond to concurrent theories, or?
Well, they are compatible in the sense that well, this one is smaller, this one is bigger, and this one is maybe the biggest. And of course, I mean, this could have like already contain this. It's just you have to look at the special case. So that this thing reduces to this and this reduces to this.
So corner symmetries imply, I mean, 3 implies 2 implies 1.
Yeah.
Already.
Yeah. It's not that implied because this like the biggest one you can have. If you put more boundary conditions, then this will reduce to this, depending on the boundary condition you have. And then if you put more things like your space-time cannot evolve, it's not dynamical, then this will reduce to this, something like this case.
Yes. Any other questions from non-experts? Any live questions?
So what is physical quantity localized at what kind of physical quantity?
Sorry.
For corner symmetry, you say
Yes.
physical quantities localized at corner.
Yes.
What kind of physical quantity?
Oh well, that's a good question. Yeah, so it's going to be like a generalization of like mass and angular momentum, but now it can depend on different points on the sphere. So I would say this factor is this part of symmetry, which is like a transformation of the sphere. So this one is like a generalization of rotation. So the concept quantity that we give you this is going to be like the generalization of angular momentum. And this part is translation. So you can think of translation as a time translation and also like a radial translation. So this will give you like a Hamiltonian of your gravity along these two directions. And this part is more subtle. It's like this part will be connected to the area of this. So it's, I mean, the concept quantity at the corner is going to be given in terms of the geometry, and you can interpret it in terms of the usual physical quantity that you're used to, like angular momentum, energy, area, something like geometrical objects. Yes.
Any example, any like a black hole, ASCP, or
Yeah. I mean, in black hole, you have the notion of time translation, and it gives you like a black hole mass. But black hole is more like this case. It also belongs to here. But in black hole, the mass cannot change in time, so it's like a static space times, non-dynamical. But in general, you can have the mass which is evolved in time, and this in the content in this layer and also in this layer. Yeah, so you can have the notion of energy in this scenario, and if you go back to like the black hole case, it's going to correspond to the mass of the black hole, which is some form of energy. Yes. Maybe I don't really answer your question. It's impossible. I'm sorry. Yeah, I mean, in terms of interpretation, it's not clear. You can interpret it in terms of the usual physical quantity you're used to, like angular momentum, energy, like linear momentum, and so on. Yeah.
Maybe his question is, so what kind of role will this large symmetry play in physical? Where
Oh, okay. Is that your question?
I don't know my prices.
Well, okay. It depends on. I mean, let's answer this or some question. So it depends on what.
I shouldn't ask, I guess.
I think we are free. There's no Heisenberg cut, and so everything is. Okay, so what do we do?
Wait,
Okay, Chris, there you go.
Yeah, because this group is so massive, and this is really, let's say, determining the one particle over space, let's say, for a acoustic quantum field theory, and then you're embedding these endodons in ordinary space-time in order to reconstruct your space. Your Hilbert space is going to be really, really massive, right?
Yes.
Inseparable and so on.
Yeah.
Well, that raises problems for the physical interpretation of quantum gravity. So, do you think there is a way of reducing them to manage more Hilberts?
Yeah, I don't know. I mean, you can pick like a subgroup you like to work to begin to work in. One that you already good this representation theory, and in fact, there's one which is called a hydrodynamic group, which is like is in some sense like this part and also like this part, but just abelian sector. And this symmetry is what occurred in hydrodynamics actually, and then people understand this better in terms of representation theory, and yes, you can classify the state using the knowledge of representation of this hydrodynamic group. So basically, you have to look at the Casimir of unitary representation. And similar to how you label this mass and spin using the Casimir of Fourier group, of Lorentz group. You can do something similar to the case of gravity. I mean, that's the whole idea. But at this stage, you can only do at some subgroup, some simple subgroup of this. So, yeah, I mean, so we definitely need help of mathematicians crack this problem. Yes.
Yeah, and any question from non-experts? No? Is that okay? So now, yeah, we accept questions from experts.
I mean, Christy is already.
Yeah, expert. Yeah. Any question?
Yeah, what if
Oh,
it's after? So what we introduce is entropy as a network charge, and
Yes.
I think it is classified to number one isometries.
Yeah.
Is there any way to generalize this notion by using the course?
Yeah, I mean, it's just the same idea, but you have bigger people. But I mean, you're going to have a charge, but whether the charge is entropy or not, that's the question. I don't know. Maybe some type of transformation correspond to the entropy. And if you subscribe to the idea that black hole entropy is the area, then it corresponds to this part of the transformation.
Okay, yeah. Well, I got two questions. One
Yes.
is you think about the higher dimensions where the two is special.
No, this because it's followed from the theorem, so it's kind of stop at correlation to objects. But I think maybe you can do more than that. I don't know. It's just open question. Yeah. For example, if your corner has a defect like a hole here, then you have to maybe to introduce the next layer of thing. And in literature, this type of defect in the corners kind of related to the fact that you have the magnetic charge. I mean, it's not guarded, it's like in electromagnetism, but it's like if you have a defect here, then you have non-zero magnetic charge. Also, it's a very interesting idea, yes, but there's no general theorem about correlation. I mean, bigger things like correlation theory and so on. Maybe there is, I don't know.
And next questions, I just understand the physical law of S. It's the
Sorry.
what's S?
S is a corner. It's just like
But it's in a concrete physical setup. Then what should I think of it? Is it the horizon or is it?
it can be anything you can choose. This is similar to you do electromagnetism and you do Gauss laws, right? So let's say if you have a electric charge here, and then you want to compute what is the value of electric charge, you just pick it's called a Gaussian surface. It can be anything, right? And this charge is given by the electric field at the corner. So it doesn't depend on the bulk, but it depends on the corners of the sphere.
We want to do the one.
And this is for electromagnetic fields, and something similar happened gravity in the sense that they are gas theories.
yeah, well, in the case of horizon, so for example, the world entropy has a very special role.
Yeah.
If we consider the surface as a horizon. So how about this case, the corner symmetry has a special role on the horizon.
What's special?
That gives so some of that the second law of
Okay, yeah. I mean, so this is just one corner, right? And then so you think of this as a surface of a black hole as like one instant of time, and then how this surface of the black hole have the quantity that correspond to the corner symmetry at the instant in time. It's going to evolve along these two directions. Like let's say this is time, this is like a radial direction. And you can recast the Einstein equation as some kind of the evolution of the charge of this corner symmetry along these two directions. But in the case of black hole space-time, I mean, there's some restriction due to the geometry of the black holes, and then you can show that it's going to obey this second law of thermodynamics. I mean, basically, it's just the Hardy equation that tells you that area has to evolve. Yeah, I mean, that case is like a special case.
But I mean, presumably you've got corner symmetries which preserve the horizon that don't preserve, say, a singularity within the black hole. So in some sense that from a thermodynamic point of view, I'm not sure.
Yeah, well, that's a good question. I don't know. Similarity is something you have to deal with. Yes, I don't know this.
And any further questions? Well, questions from online participants? Okay. Well, I have one question. Well, yeah, so in general relativity, because of the general covariance, the different morphic invariance, so well, we say that there are no local observable quantities. That's one of the difficulty to consider, well, to describe the, for example, scattering on the curved background and as well. So is this symmetry related? Well, so the people were, so for example, discuss the quantum reference frame to define such a local observable. So is this related to that direction?
Yeah, I mean, in gravity, if you want to consider a subsystem of gravity, this is the symmetry group that you have to deal with. And this one is going to be the one that your quantum definition estimate. But again, now the question is that how to deal with this huge infinite dimensional symmetry group in the context of quantum gravity. We don't know yet. People just consider like some manageable subgroup. I mean, it's just an open item. The work is progress, yes. And also, I mean, this type of charts kind of dictate that you don't have the local quantity, right? Because everything is localized on a corner. It's not a point, it's like a coordination to objects. So this is what people sometimes call it. It's quasi-local. It's just local. Yeah.
Okay. So no question.